you going?
So,
Good, thank you, James.
thank you very much.
Good afternoon, everybody. Welcome to Lecture 5 for Survey Research and Design in Psychology. So that means we've finished the first two modules. Module 1 was on survey research and survey design. Module 2 was looking at single variables, univariate descriptives and graphing, and then bivariate relationships, bivariate graphing and correlations. So in many ways that's really just been to warm you up to do the key core content for this unit, which is the knowledge you'll need to demonstrate for the lab report. So that is factor analysis. So this module is today exploratory factor analysis. Next week psychometrics, which is some follow-up bits and pieces to what we're doing today. And then module 4 will be on multiple linear regression. So it's really factor analysis and psychometrics plus multiple linear regression that you're wanting to learn how to do in the lectures, tutes, and then show us in the lab report that you've learnt how to do those things. And then we've got the final module on a few wrap-up bits and pieces and a summary. So we're now kind of at the guts of the unit. For most of you, what we do today in the lecture will be the first time you've heard about factor analysis and what to do, and it'll seem a bit weird and wonderful. But by the time you cover this content basically 5 times, which might sound like a lot, but you'll do the lecture today, go away and do a little bit of reading, so that's twice. Come to the tute, that's 3 times. Study and sit the quiz, that's 4 times. And then really it's when you come to the lab report where you'll start to go, the light bulb will probably start to go off at some point there where you go, this makes sense now, or it makes more sense than it did at the start. And that's what we're looking for, is that light bulb moment where it kind of comes together. And as I said, for most people, that's probably actually tackling the lab report where hopefully that will happen. There's several suggested readings here. Again, this is a reminder that I'm not expecting you to read every one of those readings word for word. In fact, I would suggest you don't. It's really for you to say, I need to do enough reading until I feel comfortable with what we're talking about here. For some of you that might mean skimming a little bit of all of those readings. For others you might pick a couple of them and read them in more depth. And and it's really up to you. You might feel like the lecture and the tutor are enough and you've grasped what you need to. But for most people, though, I'd suggest you also need to get at least another source of input besides what I have to say. Most of those readings are online, which means you can just go onto the Wikiversity page, click on the link, and you're there. There's a couple of readings in the reading list, and there were a few comments in the feedback, which was great. I think almost half of you responded to the survey, the ISEC survey, and gave helpful feedback. So if you're on the UC Learn page, you can click on Reading List, and there are folders there for each of the topics. So there's a folder for factor analysis, which is what you'd be looking for. I think it's about the third one down. Okay, so there's the factor analysis folder. So if I've listed that reading either here on the slides or on the Wikiversity page and it says UC Learn, then that's where you would come to get those readings. Okay, there is some new language, and in many ways I think of stats as like learning a second language or a third language. At first, it's hard to grasp until you've got a few keywords that you understand what they mean. And there's probably today, let's say 20 new words. And there is one of those readings is to a glossary on Wikiversity that has definitions for, those 20 or so terms that we'll start to introduce. So I'll give you a bit of an intro to factor analysis. One of the better ways, I think, to learn is to see some examples. So we'll look at 3 examples today and then another example next week, in addition to the examples that we cover in the tutorial. And from that point, then, you're basically best to work with your own data as the way to learn. We'll go through the steps and the process. There's a bit more decision-making involved, and probably the one thing that disconcerts most people at first is that there may not be a single right answer. There may be several possible good answers, and there may be several less good answers. And most of you have brought up with maths and stats having a definitive answer, and as things get more complex, it actually goes the other direction. It becomes a set of different possibilities. So that's one of the things that takes a little bit of getting used to here. And I'll leave the assumptions until the end. Okay, so what is factor analysis? What's it for? Where does it come from? What sorts of factor analyses can we do? Probably my favourite metaphor to think about what it is that if you're an astronomist, the universe is so big that rather than talk about individual elements like individual planets, there's millions, billions, trillions of planets, that's a lot of data to talk about. It makes more sense to group things up into hierarchical categories. So in this sense, I'm saying the universe is like, say, time management from the survey, where you've got 18 questions, or 18 planets, or whatever the smallest unit of analysis is. Maybe it makes sense that we can group up those planets that occur together in the same solar system. We could group them together. So you could think of solar systems or galaxies as factors, and there might be 3 factors. Maybe you're looking for a procrastination factor, and there's half a dozen items about procrastination, half a dozen items about planning, half a dozen items about efficient time use. So then instead of talking about 18 different planets or 18 different items, we can now just say, look, we can structure this universe into 3 solar systems or 3 galaxies. And then when we come down to the individual item level, which might be a solar system or a planet, some smaller unit of analysis, that's what we call the individual items. Okay, so it's a way of organising lots of little things into some bigger categories. So some other ways of saying that is that perhaps the variance of many variables could be largely explained using a smaller number of underlying clusters or factors, where each factor represents several correlated variables. So we're looking for sets of correlations, sets of variables that kind of belong more to each other than they belong to the other variables. So we end up calling these clusters, or these sets of correlated variables, factors. Okay, and there might be one factor, there might be lots of factors, there might be something in between. That's part of our goal, is to discover what these factors are, which items belong, and what these factors represent. So broadly speaking, factor analysis is a family of multivariate statistical techniques. I say family because there's lots of types of factor analysis, so it's a body of techniques used for looking at the correlations amongst lots of variables. And it helps us to identify where those sticky clusters of interrelated variables are, how many there are, and helps us to identify what we're going to call them. Now, why would we want to do this? Well, there's 2 basic types of reasons. Factor analysis can be really helpful for testing and building theory. The 2 examples I'll use are personality theory. How many dimensions of personality are there and what are they? Or another one would be intelligence. Is intelligence just one big thing? You're either intelligent or not, or is it many things? That's multiple intelligence theory says you can be smart with maths, but you may or may not be good with words, and you may or may not be good with your physical literacy or kinesthetic intelligence. You may or may not be good with your interpersonal intelligence, etc. So are there many dimensions of intelligence or really just one? So it can help us to explore those ideas and develop tests and measures of those different aspects of personality, intelligence, or any other psychological, complex psychological aspect of our lives. The second purpose is more practical, and that is, can we reduce the amount of data we've got? So if we've got lots of data, individual variables, why not bring it down to a smaller set of factors if a lot of those variables are correlated with each other? And that way we've got a simpler data set to work with, and we may actually have better measures because we've got measures that are built of multiple indicators instead of just single indicators. Now, often in practice we're doing a bit of both, and for the lab report I'd suggest you're probably doing some theory development. What is the structure of time management or time perspective? And you're also doing some practical, reduce all of those items down to a small set of factors that you can then use for other things, such as testing out hypotheses and relationships with other independent variables. Okay, so I've really spoken to this next set of slides. We can test theoretical models such as personality and intelligence. Most of you have done individual differences as a unit, and therefore you'd be probably familiar with the debate about how many personality factors there are. Eysenck says 3. He started off with 2 and then he added a third. The Big Five model says there's 5, but you can keep going. Cattell says there's 16 personality factors. Who's right? Well, they all actually used factor analysis to come up with their conclusions, and they've all got rationales for why they ended up with the model they ended up with. You could make up your own personality test, collect data and do your own factor analysis and maybe come up with your own model, or maybe confirm one of those well-known models. And the intelligence example I've spoken to, there's people who strongly argue for there being just one intelligence, and all those sub-intelligences are all so highly correlated that you may as well just call them little g, general intelligence. And then you've got other people arguing strongly that there is enough difference between these sub-intelligences that they should be treated separately. Again, factor analysis could help you to determine which is the better model. When we put our data reduction hat on, our goal is how do we simplify the data structure, and that includes how do we weed out poor items, items that are redundant, so 2 items that are very similar, you really only need one of them. Items that don't belong to any factor, they're kind of adding noise, so you get rid of those. Or items that are complex are items which might belong to more than one factor, and therefore they're not pure measures or clear measures of a single factor. So in a good measurement instrument, what we have are items that clearly belong to one factor but don't measure what the other factors represent. So factor analysis gives us some tools to help make those decisions about which items should be kept and retained, which items can be dropped. And then for the items that we retain, we can build composite scores, which are made up of several items and represent a person's score on extroversion, and another composite score that represents their score on neuroticism, and so on. So, as with a lot of psychology, a lot of statistics, the history of these things is about 100 years old, because that's when psychology became a science. That's when people started to apply statistical, mathematical knowledge to practical problems in psychology. However, there's a lot of complicated calculations. It actually took Pearson something like a week to do a single factor analysis with a class of students where everybody was given some bits of the calculation to do. So it would be like us working for a week full time to do an analysis that you'll be able to do with SPSS with, the click of a button in less than a second. So the usage was hampered by the onerousness of hand calculation. Since the advent of computers, and particularly personal computing, then the use of factor analysis has expanded considerably. And I'll talk more about this next week, but although it might seem a bit esoteric to you, the task of developing a way of measuring or testing a psychological variable is in high demand and increasing demand. And even if you just think about something like Australia deciding to do national testing of primary school students, NAPLAN. Now, every 2 years, every single child in Australia gets tested. Those tests have to be really well developed and standardised so that we can get national benchmarking and they're fair and equitable and so on. So the amount of time and effort that's gone into developing something like that is massive. We've talked earlier in semester about the census as a big survey exercise, personality testing in human resources. Increasingly people get pre-tested as a part of their job application, and then if they're accepted, may get further testing to work out where to deploy them. Intelligence testing in schools or ability testing, as well as psychological practice. So there is a massive demand for people to develop psychological screening and measurement tests. And there's basically no test out there, no legitimate psychological test that hasn't had factor analysis applied to it along the way. Now, I said it's a family of techniques. The broadest distinction is between exploratory factor analysis and confirmatory factor analysis. Exploratory is what we'll be focusing on, and it's called exploratory because it's reasonably open-ended. It's you basically looking at the correlations amongst the data and trying to make some decisions about a model which best captures the correlations. A more advanced or a different version of this is what we call confirmatory factor analysis. And basically, in this case, you input a model and then it tests the data against the model and gives a measure of the goodness of fit between your theoretical structure and the actual empirical structure. But that's something you tackle more at a postgraduate level. Okay, so when you do the lab report, what you're looking for, I would suggest, is a simple conceptual model. And I've basically hinted at that a simple conceptual model means that each item, and when I say item, I mean a question, item, question, variable, so a variable in your data file or a question on the questionnaire. Each one of those belongs strongly to one factor, and it doesn't really belong at all to the other factors. So each item is a pure measure of a single factor. Now, that can be contrasted with what we'd call well, I'll come to a complex model. So a practical example then is a personality questionnaire. And we find that talkative, shy, sociable and fun, the way people respond to those tends to correlate. If you tend to say I'm talkative, you tend to also, or you tend to not say that you're shy, so negative correlation. You tend to say that you're sociable. You tend to like to go out and have fun. They kind of clustered together, and we would call those things something like extroversion. Whereas anxious, gloomy, relaxed, tense are all correlated, even if they're negative. So this would be a negative correlation with relaxed. But they all have strongish correlations, and we call those neuroticism, and so on with psychoticism. So these would be good items. Say gloomy is a good item if it only correlates with these other items and doesn't really correlate with the psychoticism or extroversion items. Now that's 12 items that are going into 3 factors. In the lab report data, you've got 18 time management items, or you focus on the 18 time perspective items. In the tutes, I'll give you some more clues about how many factors you might be looking for, but it could be anywhere between 1 and theoretically 18. most likely 3, 4, 5, somewhere in there. Here's another simple model. We don't have to have the same number of items per factor. In this case, items 1 and 2 belong to factor 1, item 3 belongs to factor 2, and 4 and 5 belong to factor 3. That's still a simple model. Each item strongly maps to one factor. But this is what we'd call a complex model. Item 1, well, it's got something to do with factor 1 and it's got something to do with factor 2. It correlates with both factors. Item 2 belongs to factor 1 and factor 3, and so on. Item 3 only belongs to factor 3, but item 4 has a relationship to each of the factors. So our items are not pure measures of a single factor, they are measuring more than one factor. And you can have complex models, but what we're aiming for and what most good psychometric tests would aim for is a simple model. So the first question you're trying to answer when you do a factor analysis is how many factors best represent the data. And as I said, it can be anywhere between one factor or as many factors as there are items. So what these circles represent is 9 separate items. If those 9 items are strongly correlated with one another, they're largely overlapping, they probably just represent one factor, maybe general intelligence. Perhaps we can find 3 clusters, in this case 3 items per cluster, or maybe all of those items are uncorrelated with one another, and it's really a simple model where one item represents one factor. And then the second question, once we answer how many factors, is to which factor does each item best belong? So is being gloomy about neuroticism, or is it about psychoticism, or is it about extroversion? We need to be able to answer that for each of the items. Okay, so that's a general introduction to what it is. Let's have a look at some examples and see how it works in practice. First example is from a study which was trying to identify what are the essential facial features that we need to recognise somebody's face, and in particular to understand what emotional expression, happy, sad, disappointed, etc., is being communicated by that facial expression. So maybe we don't need the whole face. If you think about cartoons, for example, they represent just some markers, some facial markers, and communicate a lot of information just with eyebrows, eyes, mouth, etc. And you get the idea that the character is happy, sad, disappointed, etc. So what this study did was put a whole bunch of little electrode markers at multiple different points on people's faces. You can see, I don't know, like about 20 different sites. And then they got people to make different faces, express different emotions, and then this cartoon picture is the, if you like, the data, the recorded data from that face. Okay, so the the challenge or the question was, using the 20 different facial features, which you can think of as 20 questions on a questionnaire, they showed people 80 different images with those 20 different data points, and they were interested to identify what were the key ones. So there probably weren't 20, maybe we can factor analyse it down to a smaller set of facial features as being most critical. So based on an exploratory factor analysis, we're going to talk about these things in a moment, principal components and orthogonal. 6 factors were identified, and 6 factors represented about 76% of the variance in facial recognition, which is pretty good, and we'll come to what's good or what's not. It means 3/4 of our ability to recognise a facial expression is based on these 6 elements, which are position of the upper lip, position of the eyebrow, width of the nose, position of the eyes, eye and eyebrow length, and face width. Now that one's a little abstract because it's not a survey-based one, so let's just leave that one there. But I did want to illustrate to you that this isn't just for surveys. So here's an example that's probably more familiar. This is based on Victorian school teachers' ratings of different behaviours in a classroom by high school students. So teachers were asked to rate 15 different behaviours on a 5-point Likert scale. Here's some of those behaviours, but this is the way the questionnaire was presented. And this is a teacher rating each child in the classroom. Does this child not concentrate on any particular task and is easily distracted, or can they concentrate and they're not easily distracted? Mark it off. So that's distractibility. This is perseverance when things are hard, persistence versus frustration, being purposeful or being aimless and impulsive, etc. So there's 15 items, that's about half of them. And there's the other half. So the question is, are teachers dealing with 15 different behaviours here, or are there maybe 2 or 3 behavioural dimensions that summarise most of the variance in the observed behaviours? Okay, the answer to that, we're going to use the output as examples, plus you'll actually do this analysis in the tutorial either tomorrow or next Wednesday. Okay, so here's the steps to go through. Testing of assumptions, I'm going to leave those to the end. There's a fair few of them, but basically you're going to satisfy all of those with the lab report data quite comfortably. So I'm not saying they're not important, but I'm saying they're probably not the most important thing for you to be concerned with at this point in time. There are different types of factor analysis, so you need to choose your extraction method, which I'll explain in a moment, and the method of rotation. Once you've done that, you'll get some output, and you need to work out how many factors there are. There's several things you can use to help you make that decision. And with a lot of these things, you don't want to look at just one indicator, you want to look across multiple indicators to help you make that decision. Then you're going to choose which items to retain and which items to drop. Again, I'll give you some rules of thumb, but the more indicators you use to help you make your decision, the better. Then you want to be able to describe those factors in English. What do they represent? And then you can get the correlations between your factors. Oops. And finally, you look at the internal consistency or internal reliability of each factor and calculate composite scores. So you combine the items to come up with some factor scores. 7 and 8 is partly what we'll do next week. So today we're really looking at 1 to 5 or 1 to 6. First thing is that you want to put good quality data in, and this is true of all statistics, but it's particularly true of factor analysis. So if you put in garbage, you'll get factors out, but they'll probably be rubbish, and they won't be easily interpretable. So that means make sure you screen the data. The data's been out there for about a week now. I'm just starting to get messages in from people starting to ask questions and reporting things they found that don't look right in the data. So I'll start to put those back out for you. And if you keep that conversation going, then you'll make your own work easier, and you'll make everybody's work easier if you just put it on the discussion forum. And many eyes make all bugs shallow. So the more people that look at it, the more likely we are to find the errors and find ways to fix them up. So that's part of it. But the other part of it is you only want to put into your factor analysis variables that you know are theoretically related. So you only want to put in the 18 time management variables or the 18 time perspective variables. You don't want to put in the whole lot, because then you've got a whole lot of theoretically unrelated stuff. SPSS doesn't know what it's doing. It's just going to find the correlations and spit out the best mathematical factors it can. Doesn't mean that they make any theoretical sense. Okay, I thought we'd left assumption testing to the end, but it looks like it's here. So, starting with some theory, you should have some idea of what you might be looking for. I'll give you some clues in the tute, but you've got some starting readings on time management, on time perspective. If you have a bit of a read, you'll find what previous people have found, and therefore you would know that you're probably looking for 5 or 6 factors for time perspective, and you're probably looking for 3, 4 or 5 for time management. Sample size. Factor analysis is data hungry. You need lots of data. You've got plenty of data for the factor analysis, so that won't be an issue. But the rules of thumb are usually, the most commonly used ones are these minimum and ideal, that you need at least the equivalent of 5 cases per variable. So if you're trying to factor analyse 12 variables multiplied by 5, you should have at least 60 cases. That's a bare minimum. So ideally you should have more like 20 cases per variable. So if you're trying to analyse 12 variables, you probably should have 240 plus cases. So for the lab report, you'll have 18 variables to start with, multiplied by 20, 360. Even after you screen that data from 550 down to whatever, maybe 500 and something, you've still got stacks of data. Never just rely on one rule of thumb. So a second rule of thumb that you might read is that you have at least 200 cases. And again, you would meet that criteria. And there's a third rule of thumb that just rates overall amount of data. According to that, we would be in that category. Very good. All right, so lots of ticks there to say that you've got plenty of data. It's always interesting, though, to see how well does the published literature stand up to the rules of thumb, and often the answer is it's not as pretty as we might like to think. So Fabregat et al. Looked at articles published in really two of the largest psychology journals, Journal of Personality and Social Psych, Journal of Applied Psychology, and looked for articles that did factor analysis, and then looked to see what their sample sizes were. So what can we tell from that? Well, roughly 30% of the studies here, 40% here, had more than 400 cases, but that's not even anywhere near 50%. So we're actually saying that most of the published literature had less than 400 cases. And you can see that there's plenty of articles published here with factor analyses between 100 and 300. Okay, so that would suggest that maybe the published literature doesn't necessarily satisfy its own requirements for lots of data. I mean, it's still a fair bit of data, but it's not like as much even as you've got for the lab report. Next, level of measurement. The main thing to remember is that this is all based on correlations. So the assumptions for correlation apply here, and that is that you should have interval or ratio level of measurement. So the lab report data has interval measures for time management and time perspective because they're Likert scales. So that would be appropriate. Secondly, with correlations, the more normally distributed the data, the more reliable your correlations are going to be. So it is worth checking the skewness and kurtosis of each of those variables. Having said that, when you've got lots of data, the data's pretty robust to at least minor to moderate violations of normality. So we can tolerate skewness, certainly -1 to +1, almost certainly -2 to +2, and probably even -3 to +3. Outside that range, though, or getting up towards that 3, I'd be looking carefully at a variable. Maybe it's very skewed. Maybe it doesn't really belong in the factor analysis. Maybe you run it, but you've already got a little black mark against it, and you find down the track that it also is flagged as being problematic in other respects. As we saw in Tute 2, outliers can be highly influential. So again, make sure you've done a good job with your data screening, and ideally you'd look at all the scatter plots. Now with 18 variables, we're talking about a lot of scatter plots. 18 by 18, well 20 by 20 would be 400, half of those would be 200, so you're probably looking at maybe 160, 180 scatter plots to look at every single combination. That might be a bit much, but you should at the very least be checking some of those 160, 70 scatter plots. Maybe you check 40, 50 to at least have a fair chance of seeing whether there's some non-linear relationships or bivariate outliers. Okay, I'm not going to bother about multivariate outliers in the context of factor analysis, but we will talk about those when we get to multiple linear regression. A lot of people come up and go, well, I've got an outlier, what do I do? Well, the simplest answer is run your results with it in, and then run your results and remove that case or that bit of data, and answer the question for yourself, is there any difference? If there's no difference, no practical difference in the results, it's not an influential outlier. So you may as well keep it in. If you are getting some profoundly different result, then you've got to scratch your head and go, look, this is affecting the results, so am I going to keep it in, or am I going to take it out? And so we are assuming linear relationships, which is why you want to look at your scatter plots. A set of correlations should be what we call factorable. There's a whole lot of fancy technical stuff here, but really all it means is, are there enough correlations amongst the data that it makes sense to even do factor analysis? And the answer is almost certainly yes, because we've used questions that we know from the past are correlated with one another. But to test that statistically, there's 3 different ways you could do it. One is you just stare at the correlation matrix and check that there are some correlations above about 0.3. Doesn't have to be all of them, just some of them, and that would suggest that there's enough going on there that you're going to find some clusters. Or you can use something called the anti-image correlation matrix, and you want diagonals above 0.5, or you can just use one of these global indicators. So if you get a significant Bartlett's test or a KMO above 0.5 or 0.6, that shows that it's factorable. You don't need to do all of those, just one of them is enough evidence that it's worth proceeding. So these SPSS output screenshots are from those classroom behaviour, from the classroom behaviour data. Here we've got just the correlations amongst 5 variables, and I can quickly see 0.7, 0.7, 0.5, 0.4. There's lots of correlations above 0.3. So yeah, I'm happy to do factor analysis with that data. If I want to use the anti-image correlation matrix, the output will look like this. And I'm looking at the diagonals to see if they're over about 0.5 or 0.6. They all are, clearly. So again, it's highly factorable. And then the final way you could do it is with these global measures of sampling adequacy. The KMO, or the Kaiser-Meyer-Olkin, is above 0.5 or 0.6. Or the Bartlett's is significant. So in your lab report, you just want to show that you use one of those techniques to prove or demonstrate that there were enough correlations to proceed. Okay, so you've satisfied the assumptions. You've got 2 decisions to make before you can generate some results. There are 2 methods of extracting the factors. In practice, they're reasonably similar, but there is a kind of theoretical distinction between them and a mathematical distinction. So method 1 is called principal axis factoring. The key thing is that when it looks for the factors, it's only analysing the variance that's shared amongst the variables, as opposed to principal components. It analyses all the variance and tries to find factors. So why use one or the other? Well, generally we say that if you have a theory-driven purpose for your factor analysis, and usually that just means what are the factors and how do they relate to one another, then you would tend to use PAF, principal axis factoring. If your purpose is more practical, you're trying to reduce the number of items down to a small number of factors to calculate composite scores, to then use those scores for other analyses, probably use PC, principal components. Now, sometimes you've got both purposes, and the lab report I'd suggest has both purposes. In that case, I'd suggest principal components. So we'll do a bit of both in the tute, but when it comes to your lab report, I'd suggest it's not wrong to use PAF, but I suggest you use PC. In practice, you would come to similar sets of conclusions with either approach. Okay, so this diagram just tries to represent that up the top it says total variance of a variable, so the whole box, the whole rectangle, think of that as 100% or all the variance of a variable. Some of that variance is shared with the other variables, so that's the part that overlaps with other variables. If you were doing PAF, that's the only part of the variance that's analysed, just what it has in common with other variables. If you do PC, then it'll analyse both that common variance and the variance that's unique just to that individual item. And the other thing is you can try both. And I'd encourage you to try your factor analysis different ways. Chances are it's going to point you in the same sort of direction. But if you get very different solutions, you might try and work out why and decide on which approach is more appropriate. So the goal of our factor analysis is, if you like, we're starting with all the variance or all the shared variance. We want to explain most of that variance, or a good chunk of it, just using a relatively small number of factors. In practice then, we're probably hoping to explain over 50% if we can, maybe up to 75% of the variance, with quite a small, relatively small number of factors. So we're not trying to explain everything, we're just trying to find a sweet spot where a small number of things explains a relatively large amount. So here's the output, or part of the output from our factor analysis of classroom behaviours. You'll get a closer look at this in the tutorials. The point for now is that we started with 15 items. If we choose 3 factors, we can explain 73% of the variance. Well, that's pretty good. You know, if I'm a classroom teacher and I'm dealing with a whole bunch of rowdy, difficult to manage, as well as some introverted and, you know, lacking confidence kids, to try and think about 20 kids and 15 behaviours, that's just cognitively, you know, impossible. But if you could tell me as a teacher that, you know what, if I just focus on 3 behavioural dimensions, and it captures about 3/4 of the behaviour in the classroom, I'd go, great, train me up on dealing with 3 behaviours, and I can put that into practice. So that's what we're trying to do, is we're trying to do a lot of the variance with a small set of factors. Now what we're starting to do is see some of the output that you'll get, and factor analysis does produce a lot of tables and output. We'll go over those in detail in the tutorials. As well as getting the factor level information, we're going to get item level diagnostics or information. And one of those is what we call the communality. The word is a bit of a clue. Commune, or basically how much does each variable have in common with the factors. Now, if you think of it like this, that each variable puts in, if it's PC, puts in 100% of its variance. And if there's 15 different variables, each one puts 100% into the kitty, or sometimes I think of it as each variable's put in $1 into the kitty, 100 cents, $1 each, and there's now $15 sitting in the kitty. Then when we extract the factors, we might pull out 3 factors, and it explains, say, 50 to 75% of the variance. How many cents from each of the variables are accounted for by the factors, and that's the communality. So hopefully each item has at least 50 cents or 0.5 accounted for by the factors, and that's reasonably good. You may have variables where less than 0.5 of the variance is accounted for by the factors. And it's not the end of the world, but they may be items that you're a bit concerned about. If you want to have higher communalities, you might need to extract more factors, or perhaps this is an item that you're going to end up dropping because it is not well covered by the factors. Okay, so it's worth just noting those items. Don't necessarily do anything about it now because you're going to get more information, but if you get a few black marks against an item, you might go, this is a better model without that measure. So here's a table of communalities for the 15 behaviours, and looking down the right-hand column here, you can see they're all between 0.5 and 1. So the 3 factors do a good job of accounting for most of the variance in each of the items. Okay, the next useful piece of information we get are what are called eigenvalues. Now I mentioned before that we've got $15 sitting in the kitty. Factors are very greedy things. So the first factor comes along and it pops its hand into the kitty and it grabs as much money as it can. And it pulls out all the money it can, opens up its hand, and let's say it's got $8 in its hand. Well, that would be its eigenvalue. It would have an eigenvalue of 8. Now that means we know there's $7 left in the kitty, so factor 2 is going to come up and say, I'm going to grab as much as I can. And it brings its hand out, and maybe it's got $4 in its hand. So it's got an eigenvalue of 4. And this process keeps continuing. Maybe the third factor gets, $2, and then we're getting down to cents. Fifth factor gets 50 cents. Sixth factor gets 20 cents. And you get down to the last factor, and there will be as many factors theoretically as there are items. So we get down to the 15th factor, and there might be a couple of cents left, and that's all it gets. So in a sense, all we're doing is we're redistributing or redividing the variance from each item amongst some very greedy factors. And what we're then interested in are the big fat factors, the ones that are the richest, that explain the most variance. And we're not that interested in the ones that just explain a few cents. Okay, so my explanation there is just a slightly less technical version of what is written here. One rule of thumb for how many factors to extract is something called Kaiser's criterion, which says to extract all the factors which have eigenvalues over 1. That's a nice simple model. It doesn't always work, because you might have a factor that is worth 97 cents and it's got a whole lot of other things going for it, and you might choose to keep it. And you might have another factor that is worth 1.2, but when you look at it, it's just a pile of garbage. But as a rough starting point, eigenvalues over 1 is about a good place to be choosing how many factors to extract. So we had this table up before, but we were looking over here. Now we look back at the left-hand side, and this is the list of eigenvalues for each factor. So factor 1 got $9.35, factor 2 got $1.52, and then factor 3 got 93 cents. So we dropped below 1. Factor 4 got 46 cents, and so on. So we have eigenvalues ranging between 9.36 and 0.15. 2 factors would satisfy Kaiser's criterion, but the third eigenvalue of 0.93, as it turns out, is a useful factor. That's based on subsequent information. We also note that there's a pretty sizable drop from 0.9 down to 0.4, and then we just go 0.4, 0.3, 0.2, etc. Now that idea of there being a sizable drop is also a useful idea, so much so that it's helpful to graph these eigenvalues. So we can get something called a scree plot, which is a graph of eigenvalues, and that helps to give us a visual diagnostic on where we might draw the cutoff. So there's the first factor, 9.3, second factor, 1.5 something, might have been more, third factor, 0.9, and then we were down to 0.4, 0.4, 0.3, etc. So it's called a scree plot because you can think of this as the main factors form the cliff. And what do you find at the bottom of the cliff? You find the rubble that fell off the top of the cliff and landed at the bottom, and that's just all little bits of crumbly bits of rock that aren't that useful. What we want is the cliff. We want the main structure. The tricky part then becomes, where do you draw that cutoff? So is 2 factors part of the cliff, or is it part of the rubble? Is 3 factors part of the cliff, or is it part of the rubble? Well, clearly 4, 5 onwards, that's all just the flat rubble at the bottom. The factors 2 and 3 are a bit higher, and they do seem to form part of the vertical structure. But it's not definitive. So the scree plot really just helps you to get into the ballpark. So when I look at that, I see, okay, it's definitely 1, it's definitely not 4, so I'm probably looking at 2 or 3 factors, and I'm going to look more closely at the 2 and 3 factor models. Okay, so the scree plot's good for screening out non-solutions and narrowing down to a small set of possible solutions. This is a different scree plot from a different data set, just to show you that you'll get different patterns. And what's notable about this is a bit like personality, where you might have 3 factors, you might have 5, you might have 16. With this data, you can see here we come down, and there's a drop-off from 3 to 4. And then you can see another drop-off down here at sort of 7 to 8. So the drop-off occurs after 8. So in this case, I might be looking at maybe 3, or maybe I look at this 5, or maybe 8. So I'm looking for where there's a sudden drop. Yeah. Yeah, so the question is, how clear are these scree plots going to be? Like I said, some of them will give you a really clear answer just from one scree plot. Others will be a bit vaguer, and that's normal. It just depends on whether there is a really clear factor structure. If you've got a really well-developed questionnaire, you'll probably see something quite sharp and dramatic. If you've got a set of not so well developed items, then you'll get a more rounded elbow rather than a sharp elbow, and that's telling you that you're going to have to do some work and you're just going to have to look more closely at 2, 3, 4, 5 factors. And you can't use the scree plot in that case on its own to make your decision. You're going to have to look more closely at the factor loadings, etc. So it's just sort of an initial guide, I guess. Okay, there's something else I didn't probably explain, was that if you add up these eigenvalues, they will always equal the number of items. And that goes back to what I said earlier. Imagine that each item is putting in $1. That's its eigenvalue. Then if you add up the eigenvalues, it's going to equal the number of items, the $15 we put in originally. So knowing that, we can then work out these percentages of how much variance explained, because this is the 62% is 9 out of 15, 10% is 1.5 out of 15, etc. And if you then combine those, you can get the cumulative percentage explained, and of course that would add up to 100%. So if we extract 15 factors, we explain 100% of the variance. Now, knowing that, you should be able to work out a quiz question that might appear like this. An exploratory factor analysis has 20 variables. Okay, well, it's going to have 20 eigenvalues if it's got 20 variables. We learn that 4 factors explain 60% of the variance. What do the eigenvalues of factors 5 to 20 add up to? Well, if the first 4 factors explain 60%, eigenvalues 5 to 20 explain 40%. 40% of 20, well, 10% is 2, so 40% is 8. So the eigenvalues from 5 to 20 must add up to 8. B. Okay, the idea of that type of question is really to check whether you understand the relationship between the eigenvalues and the percentage of explained variance. Okay, so if that doesn't quite make sense, ask me in shoots and I can go over it more slowly with you. Okay, so we're still trying to tackle the first question, first challenge in our factor analysis, which is to decide how many factors are there. First thing is, it is a subjective decision. It's possible that one person does a lab report that says there's 5 time perspective factors, and that's an HD lab report, and somebody else puts in a lab report that says there's 6 time management factors, and that's an HD lab report. So that there is a degree of subjectivity, and sometimes the answer is that there's 5.5, but we can't have half a factor, so it's just that one person has accepted that half a factor as a complete factor and one person hasn't. Remember, the overall goal is you want to try and explain as much variance as possible, but we're not trying to explain 100%, because we're just trying to use a small number of factors. So things to take into account. Can you go back to your lit review, to your theory? What did other people find? And therefore, what are you probably looking for? Now, we don't want to be too railroaded by that, because we might find something different from what people have found in the past. Perhaps what's been done in the past has been done in America 60 years ago, and in Australia in 2018, people are thinking differently. Nevertheless, it gives us a hint or a guide. Second clue might be, what if you used Kaiser's criterion and said, how many factors have eigenvalues above 1? That's another clue. But it might not be perfect. You might want to go a bit below or a bit above. Thirdly, where's the drop-off in the eigenvalues? So using the scree plot, can you separate the cliff from the rubble? Fourthly, the weakest factor is going to be your last factor. So look very carefully at the last factor. If you're extracting 6 factors, look at factor 6, look at the items that belong to it, and ask yourself, do they belong together? Can I say what they represent, or is it just a seemingly random set of 3 items chucked together? If you can't make sense of the last factor, it probably doesn't exist, so come back to one less factor. So what you'll be wanting to do is looking at probably factor models, one above and one below what you think you've got. So if you think it's 5, have a good look at 6, have a good look at 4 before you settle on 5 being your preferred solution. Okay, there's no point, the last point here, number 6, there's no point in having a 6-factor model if you can't explain what those 6 factors are. So can you label them? Can you describe what they represent? Okay, so we've said 50 to 75% of the variance, using maybe a quarter to a third as many variables. If you're starting with 18 variables, then maybe 3, 4, 5, 6 factors. Watch out for the weakest factor being meaningless. If that happens, roll back one model. And keep checking the meaning of the factors. So a common mistake here is that people get very statistically focused. We haven't looked at the factor loadings yet, but we're going to in a moment. And they go, look, I've come up with a perfect model. I've got all these beautiful numbers. And then they say, well, what is factor 3? I don't know. So you need to be constantly looking back at the written items so that you understand what factor 3 might be representing. Because if those items don't seem to go together, then you're going to have a hard time saying what factor 3 actually is. So the missing piece of the puzzle in the output is what we call a factor loading matrix. And this is going to list each item and each factor, and you're going to get the amount that each item loads onto each factor. And this is the single most useful piece of output that you'll get. However, until it's rotated, it's not that easy to read. So because we said that the first factor was very greedy, it really was not thinking about the second factor when it just grabbed as much money as it could. Similarly, the second factor was not thinking about the other factors when it just grabbed as much as it could. So what we do is we rotate the factor structure so that it evens things out a little bit better amongst the factors. So a metaphor that works for me anyway. I grew up in the 70s, so we had lots of board games before there were computers, and we played a game called Kerplunk. And what you did was you stick a whole lot of sticks in through the net or the column, and once you've got enough sticks in there, you can pile a whole lot of marbles on top. And then you all take turns, one at a time, taking out a stick, and the goal is not to let anything fall. Now you can think of these 15 sticks as the 15 items, or sorry, the sticks as the factors, so that you start off with 15. You don't really need 15. You could pull out 1, 2, 3, 4. You can probably hold up most of those marbles or explain most of the variance just with 6, 7 well-selected sticks. If you pull out the wrong one, if you pull out factor 1, the whole thing comes down, or most of it. So it's a similar sort of thing. You're saying, which factor can I do without? I don't really need it. Don't really need it. Don't really need it. I just can explain most of the variance. I can keep up 80% of the marbles with 4 sticks. And that's the kind of solution you're looking for. Okay, so there are 2 ways to rotate the factors, and they are either orthogonal, which SPSS calls Varimax, and what that does is it tries to keep your factors to be uncorrelated. So if you think of personality, personality theoretically has uncorrelated factors. If I'm extroverted, that doesn't necessarily tell you anything about how conscientious I am. They're fairly uncorrelated. Okay, so if you think your factors should not be related or not very related to each other, you want to try orthogonal rotation. On the other hand, if you think your factors might be correlated, and intelligence is more like this, because if you're good at maths, you're probably good at English as well. It might not be a strong correlation, but you probably, tend to be better at other academic tasks. In that case, I'd be doing oblique rotation for intelligence because I'm going to allow my factors to be correlated with one another. Now, when you start, you might have no idea. So you've just got to pick one. And the starting point I'd suggest is to go for oblique. So it's called oblique rotation in general. SPSS calls it Obermann rotation. So if in doubt, start with oblique rotation, mainly because it will tell you then how correlated your factors are. And if it tells you they're not correlated, then you can switch over to orthogonal. Now, a little bit like the methods of extraction, PAF or PC, you will get similar solutions, but it will actually be more obvious that probably that one is superior to the other one. And we'll look at that more closely in tutorials, how you can make that decision. So the key thing out of this slide, and I'll emphasise it in the tutes, is that if you find that there are correlations more than about 0.3 between the factors, you'll find you're better off with oblique rotation. If you've got correlations less than about 0.3, you'll be better off with orthogonal rotation. In practice, try them both out, see which one works best. Okay, I've already emphasised this to be guided as much by theory as you are by stats, or interpretability, at least as much as the stats. Okay, so back to these factor loadings. We're looking hopefully for a simple factor structure. Remember we started early with that? Each item loads strongly onto one factor, but not onto the other factors. Our factor loadings can range between, just like a correlation, -1 and +1, with -1 or +1 being strong, 0 meaning that it really doesn't load at all. So a strong loading is anything above about 0.4, but probably more like 0.5, 0.6. So a weak loading is really anything below about 0.4. Now, preferably, but not always, we would like a factor to have more than one item. So ideally we're hoping to have factors built of, say, 3 or more items. Doesn't always happen. So here's the factor loading matrix for the classroom behaviour data. This was a PC, principal components, and it's Varimax, which means it's an orthogonal rotation, so we're looking for independent or uncorrelated factors. Okay, so what are we looking at here? Well, we've got factor 1, 2, 3 across the top. We don't know what they are yet. We've got the items down the left-hand side. And where I've drawn these coloured lines indicates where I'm seeing high loadings. We have also sorted this so that we've got the highest loadings on factor 1 up the top here. So I'm getting the sense here that there is a factor. So this is 0.8, 0.8, 0.8, 0.7, 0.7. And if you look at the cross loadings, so Persevere loads 0.8 on factor 1, 0.1 on factor 2, and 0.2 on factor 3. So Persevere belongs strongly to the first factor, and it doesn't really belong to factors 2 or 3. I've actually suppressed loadings below 0.1, so where there's a blank, that's 0.0 something. So second one, 0.8, 0.0 something, and 0.3. So there's a gap in the loading from 0.8 down to, say, 0.3. There's a gap of about 0.5. Clearly these items belong strongly to one factor and not really to the other factors. What is factor 1 then? It's about behaviours where a student is persevering, curious, focused on their activity, concentrating, paying attention. Well, if you blend all of those together, what have you got? You've got a student who can concentrate and focus on a task. If you don't know what to call a factor, then consider using the top loading item, because that's the strongest item. So maybe I call this task perseverance. All right, then factor 2 seems to be made up of, and I'm kind of ignoring the 0.1, 0.2, 0.3, then I see 0.8, 0.8, 0.7, 0.6, 0.6, and then we're down to 0.1, 0.2. So factor 2 is made up of these blue items. We're talking about students who are placid, calm, relaxed, compliant, self-controlled. So this is the dimension of a child being relaxed versus agitated, okay, or chilled out versus, intense. And then factor 3, a little bit harder to see, but we've got 0.7, 0.7, 0.7, 0.6, 0.6, if we just count the bottom 5 items. These are students who relate warmly to others, they're contented, they're cooperative, even-tempered, communicative. So this is a bit more about sociability. They're socially warm and, cooperative versus, uncooperative and cold. So I feel like I can identify 3 distinct dimensions of behaviour. However, there's a little bit of a problem with these 2 items, compliant and self-controlled, because when I look across this way, 0.2, 0.6, 0.5. For this one, 0.4, 0.6, 0.5. So these items kind of want to be a little bit about calmness, factor 2, and they want to be a little bit about sociability, factor 3. These 2 are complex items because they belong almost equally to each factor. Okay, being compliant is partly about being calm, but it's also about being sociable. Being self-controlled is partly about being calm, but it's also being controlled in a social context. So if I want a simple model, I'm probably going to rerun this 15-item factor analysis and take out these 2 items and just run it as a 3 13-item factor analysis. So if we adjusted our minimum criteria for the target factor loading to be 0.6, we would keep that item there, compliant, but we still have the problem that it still wants to load almost as much on the other factor. And if you use the cutoff here, 0.6, you could just drop that item out altogether because it doesn't have a target loading of 0.6. So the suggestion would work for that second one. You've probably still then got one complex item left. Okay, now the other thing is that we've used Varimax rotation here, and you'll see that when we do a Oblerman rotation on the next slide, you'll see a lot less cross-loadings. Okay, so look how many numbers are on this screen, and look how many numbers are on this screen. Fewer of them. So all of these blanks are now factor loadings below 0.1. So they're 0.0 something. I'll go back. So there's our factors, lots of little cross-loadings, but here, even fewer cross-loadings. Now that is evidence that our factors are actually correlated, because when we allow them to correlate, doing an Oblerman rotation, SPSS was much happier with that, and it had fewer cross-loadings indicated. Now the factors have been reorganised. You see the colours the other way around. Up the top we've now got sociability, then we've got the task perseverance, then we've got the calmness. What happened to the two complex items? They're down the bottom, and they're still complex. 0.47 versus 0.52, 0.4 versus 0.4. The suggestion that was made about using 0.6 as the minimum loading cutoff would work in that you would remove these, but you'd not want to get too religious about it because you would then lose this item, 0.596. But it's even more obvious now that these items really do not belong. So what we should have on the next slide is the same thing without those two items. Item factor analysis with Oblerman rotation, so it's correlated factors. And now things look a whole lot tidier. Almost all the cross-loadings are below, might be 0.2. We might have suppressed below 0.2 there. So they're 0.0 something or 0.1 something. And if I look at these cross-loadings, there's still a big gap, 0.7 versus 0.2, 0.7 versus 0.3, 0.7 versus 0.3. Even more importantly, I can make sense of each of those three factors. So that's a good example of what you're wanting to head towards doing with the lab report. You'll start with a few more items, so you start with 18. Probably you'll drop a couple along the way. You might have more than three factors, but similar sort of process. Now, it's because we're dealing with complex, multiple correlational relationships, it's very tricky to get a graph. So whilst I've been trying to drill into use graphs, the best we can probably do is you can get a 3D scatter plot if you've got three factors. But even then, that's tricky to look at. If you stare at it, you can see that there are three factors on the three different axes. But if you end up with 4 or 5 factors, very tricky to look at. So you really do need to rely on your tables of factor loadings. So once you've decided how many factors, you're starting then to look at which items belong to which factor, which we've kind of been doing. You can have a factor with one item. That's the minimum. But preferably you've got multi-items within a factor. So that would mean you'd need at least 2, and most factors in a well-developed questionnaire would have at least 3. But there is a law of diminishing returns, so 12 item factor, you could probably do that with 10 or 8 or 9 items. I like to think of it as sort of the roundedness. If you think of different dice, a normal 6-sided dice, if you roll it along the ground, doesn't roll that well. It's got 6 sides. If you get a 10-sided dice, it rolls better. If you get a 20-sided dice, it rolls even better. So what you're trying to build is a rounded measure. So you're trying to measure different aspects of the one behaviour or the one attitude. But there's less and less value to adding a 21st or 22nd or 23rd item. So we start, when we were looking at the factor loadings, we're starting to talk about why you would eliminate an item. You might set some sort of minimum loading for the main target, whether it's 0.4, 0.5, 0.6, somewhere in there. You might consider what the maximum cross-loading is that you're prepared to tolerate. And I'd suggest you probably don't want cross-loadings above about 0.3. Or, as you saw me doing, if you combine those two things, you're really looking for distance or a gap between the primary loading and the cross-loadings. But keep checking the meaning of the item and whether it belongs to the factor. When you're eliminating items, I would take out the worst one and rerun your model. Because when you do that, all the numbers get recalculated, and some things that were marginal may now look worse, or they may look better, but rather than just taking out a whole set of items at once, you won't really see it progressing. So try and take out one at a time, rerun it, then look for the next worst item, take it out and rerun it, and so on until you think you're done. Sometimes when people do that, it's a bit like pruning a tree. You can get a bit carried away and you go, oh, it was a beautiful tree to start with and now I've just got a stick and I chopped off too much. And that's okay. You just go back again and you start again and you go through it. So, yeah, don't get too savage. You can be maybe a bit more savage on factors that have a lot of items. So if you've got 9, you can be a bit more savage and prune it down to 6. But if you're only starting with 3, you don't want to get too savage with that factor. Some rules of thumb. There's one ranking of the primary target factor loadings. And that would suggest you want to be, probably 0.5 and above. The other thing is I'd be looking for the gap. So if the top 3 loadings are 0.8, 0.7, 0.6, and then you've got items on 0.3, 0.2, that's probably a good place to draw the line. Okay, so in practice, you'll get your 18 items. You'll choose PC or PAF. Probably I'd suggest PC. You want orthogonal or oblique rotation. I would probably start with oblique. Then you're wanting to say how many factors are there and look at several different runs. Look at 2, look at 3, look at 4, look at 5, etc. Eventually you'll settle on 1, say 5 factors, and then you'll start to look more carefully at the items and start taking out the weakest items out of your model. So take out your items one at a time. Don't be overly concerned if your solution is different to somebody else's. Remember, you might have done your data screening differently, and there may be more than one good solution. But have a conversation with them and ask, what's I've only got 4 factors, you've got 6. How did you end up with 6? Because I've only got 4. Maybe you learned something from what they did. You don't need to do this, but it's just to point out that if you were developing an intelligence questionnaire, you would then run your model across various subgroups. So you would say, does my 5-factor model work for females? Does it work for males? If it doesn't, then you might need to go back to the drawing board, because we want our intelligence method to have the same structure across males and females. Maybe test it across children and adults to see if you've got the same structure. Yeah. Against last year's data set? Look, yeah, no, you could, and I think I've left last year's data set up there, and you're right, it was the same questionnaire. So that's actually a really good thought. You come up with a 5-factor model, you might want to download last year's data set and run it. The only problem is you'd probably have to screen it, but now that you've mentioned it, I could put up the screen version of last year's data. So I'll try and do that. Yeah. So anything like that to try and say, well, have I just built my model on this data set and it doesn't really work across subgroups or in other situations? You'll then go on to analyse the internal consistency for each factor. We'll cover that in next lecture. And then you can create composite scores and go on to do multiple linear regression. Okay, so here's one more example of scale development and factor analysis. So this is for something called the condom use self-efficacy scale. By now everybody's gone to sleep, so this usually wakes them back up. What is condom use self-efficacy? Well, self-efficacy is your belief in your ability to do something, particularly in a difficult situation. So this is a 10-item measure of people's belief in their ability to use condoms. Administered to 447 college students. Factor analysis with principal components and vary-max rotation. So we're looking for uncorrelated factors. So out of those 10 items, there were 3 factors. Appropriation, which is getting hold of them. Second factor was what it indicates or doesn't indicate about whether you've got an STD. And third factor was how you handle the perception that your partner may disapprove of using them. Okay, so factor 1 had 4 items. Now we've only put here the primary loading, so factor loading 0.7, 0.6, 0.6. And if you read the items, then you can see how they belong together. I feel confident in my ability to put a condom on myself or my partner. I feel confident that I can purchase them without feeling embarrassed. I feel like I can remember to carry one with me should I need it. And I like this last item. I feel I could gracefully remove and dispose of a condom after intercourse. Okay, so they're all about feeling cool with getting hold of them and using them. Second factor, 3 items. I wouldn't feel confident suggesting using a condom with new partner because I'd be afraid he or she would think I've had a past homosexual experience. Second one, I'd be afraid that they'd think I have an STD. Third one, I'd be afraid that they would think that I think they've got an STD. Okay, so that's that condoms are sort of tainted with stigma. How confident do you feel in negotiating that stigma with pretty strong factor loadings? Third one, 3 items, navigating partners' reactions. So I'd be afraid that a partner would reject me if I suggested a condom. I'd be unsure of my partner's feelings about using one, so I wouldn't suggest it. And if I basically wasn't able to successfully use one, that it would be embarrassing. Okay, 0.7, 0.6, 0.6. So I think that's a really good example. You can see that there's 3 distinct factors that are relatively uncorrelated. Just because you feel good about one aspect of navigating condom use, you may not feel so confident about another aspect. And there's reasonably good loadings. We don't actually want super high loadings, because if these are all super high, the only way you can get them really, really high is that you have almost identical items, so they're kind of redundant items. You do actually want some spread and some diversity that are getting at different aspects of that underlying factor. Okay, so I'll talk in the shoots a bit more about what structures might be expected in the questionnaire, but this is a little bit about the Zimbardo time perspective inventory. Those who have already done motivation and emotion may remember this, because you would have actually done it yourself in the tube. So the original version had 56 items, administered to 600 college students. There were 5 factors, but they only explained 36% of the variance, which isn't all that much. There was a big drop in the scree plot between the 5th and the 6th factors. Those 5 factors were negative thoughts about the past. Secondly, present hedonism, which is seeking of pleasure in the present. Third factor was focusing on the future, about what's going to happen next, what you're going to do in the future. Fourth factor was past positive, so feeling good about your past. And fifth factor was past, I've got a repeat there, haven't I? Two past negatives. This is mislabeled at the end, so this would be yeah, can't quite think of the name of it, but it's not past negative. Present fatalistic should be that last one. So this is from the original kind of article. You don't need to read it, but there are the 56 items, and there's the factor loading, so you could see them. They've actually bolded, I think, the primary or strongest loadings. There's a table of the correlations amongst the factors. What you should get from that is that they're fairly uncorrelated. That's why an orthogonal rotation should have been used, which it was, very max. So what you've got in the survey is the short version of the Zimbardo time perspective inventory, but it is trying to replicate 5 factors. Having said that, you should find an article that has used it and found 6 factors. So the debate is really between 5 or 6 factors. Okay, so in summary, factor analysis is a toolkit for analysing multivariate correlational data for the purpose of identifying clusters of covariance, and we call those things factors. The steps you go through: test the assumptions. It's almost a given, but you want to write those steps into your lab report. PC or PAF, probably use PC, principal components, because you want to build composite scores and use them in your MLR. Rotation, orthogonal or oblique, I suggest or oblique. I suggest you start with oblique, which is oblique in SPSS, so that you start with correlated factors, find out how correlated they are. If it's less than 0.3, go back to orthogonal rotation. Task 1 then is answer the question, how many factors? You can use eigenvalues, you can use theory, you can use the scree plot, and you can look at the target variance explained. Then work out which items to keep, which items to leave out, dropping the items one by one, particularly if they're complex. Make sure you can name and describe your factors, get the correlations between the factors, and then we'll look at reliability and composite scores next week. Key things for assumptions: minimum 5 cases per variable. You need to know how many variables, multiply it by 5. Preferably 20 cases per variable, number of variables multiplied by 20. Be aware of outliers. Look at both your scatter plots and your histograms of individual variables with the skewness and kurtosis to see if you've got anything really wacky in the data. PAF, good for theoretical data exploration. PC, good for data reduction. Orthogonal, uncorrelated, oblique, correlated factors. I'll just mention those. Make sure you know what criteria, because you want to report your criteria in your results section for how you decided to keep or drop factors. You can kind of come up with your own criteria. The main thing is don't use any one criteria on its own. Use a blend, use a combination to try and come up with well-considered decisions. All right, folks, hopefully see you in Toots tomorrow or next week to do factor analysis, and then we'll move on to psychometric instrument development in the next lecture.